Hello! If you made it this far, the end is in sight. Final exam's coming up. It's a lot to remember, but that's what those note cards are for, right? And practice, practice, practice. That really makes a difference. So this problem starts the beginning of the brand new material. So this is where it stops being review from midterm 1 and midterm 2. And now it's kind of new material that we haven't been tested on yet. So this is probably what you would want to focus on, these problems from here to the end. And then when you kind of feel all right about that, then I would kind of go back and review the old stuff. And you probably don't need to study that as much. You just need a refresher maybe, just to see, what you've forgotten. Are there any formulas that I need to write down? Things like that. So, all right, let's get started. So it's problem number 159. It seems like a very high number, right? But a lot of practice, I guess, is better than not enough practice? I don't know. I hope so. But let's see. So we want to add these rational expressions together, but they don't have the same denominator. So we have to find the least common denominator. And in order to do that, we need to factor their denominators, if they do factor. So the left rational expression here has a t plus 1 as its denominator. That's as simple as it gets. It can't be factored any further. So I'm going to try to factor the rational expression on the right's denominator, t squared minus 1. That's a difference of squares. It can be factored into t minus 1, t plus 1. Okay, now looking at these two denominators, I can kind of tell they have this factor in common, t plus 1. So the least common denominator is going to definitely have that factor. But then any other factor that I see between the two factorizations as well. The t minus 1 as well. I'll need any factor I saw. And remember, you need any factor you see the least number of times you see it. And I only see t plus 1 once here and once here. So I would only need one of those. Same with t minus 1. I only see one of those as well. So okay, there's our LCD. I just got to look at the denominators and see what do I need to multiply each one by to get there. The first one I need a t minus 1 since it already has a t plus 1. Oops, I put a plus when I was supposed to put a minus. There we go. All right, and then the second denominator is already perfect. It has the t minus 1, it has the t plus 1. So there's not really a need to multiply it by anything. See, I might multiply out the numerator here. It's t times t, which is t squared. T times negative 1 is negative t. And now it has that common denominator, t plus 1, t minus 1. And we've kept the second rational expression the same, so I'll just kind of rewrite it. All right, now that they have the same denominator, I'm free to combine these two fractions into one. So if you want, you can take an extra step and say, okay, I'm going t squared minus t, and I'm adding the numerator of the second rational expression, which is a negative t. I didn't really have to put that in parentheses, but I guess having a plus and a minus next to each other is kind of weird, so I did. And then they have the same denominator, t plus 1, t minus 1, and it doesn't matter what order you put those two in. And then in the numerator now there are some like terms. The negative t and the negative t make negative 2t. And notice that I'm not multiplying out the denominator because the last step you want to do is to factor everything to see if you can reduce the resulting rational expression when you're done adding or subtracting these guys. So if I multiply the denominator out, that would kind of defeat the purpose. I'd have to refactor it again later anyway. But at this point, to see if it reduces, I'd like to see if this reduces, but remember that you can't reduce until everything's factored. So I better factor the numerator. And the numerator, it looks like both terms have a t in common. I'm going to take a t out. If I factor t out, t minus 2 is left. And the denominator is already factored, so there's no need to really do anything with that. Looking at this now, I notice that the numerator and denominator have nothing in common. There are no factors that are like. So that's as good as it gets right there. All right, so that's pretty much how these are going to go. This next one should go similarly. It might be a little more complicated. We'll see. But it's the same idea. So the second one now, number 160, we are subtracting. So I have to be maybe a little more careful. But the same idea first. We want to first factor the denominators to see what the LCD will be. The first denominator is a difference of squares. It'll be x minus 5x plus 5. And then we're subtracting the second rational expression. I'm going to leave its numerator the same. The denominator, though, factors into x minus 5, x plus 1. And of course, remember that those factors don't have to be in that order. It could be x plus 1 on the left, x minus 5 on the right. It doesn't really matter. All right. Now that I see these denominators, I can tell the LCD should have each of those factors. I see an x minus 5 as a factor. I see an x plus 5. The second denominator kind of gave me an extra x plus 1 factor. But I don't need two x minus 5 factors, even though I see it in both factorizations. You notice that it only occurs once in the first one and once in the second one. It's only if it occurred twice in one or the other, or more than that, that you'd need more than one of those factors. Now that I see the LCD is x minus 5, x plus 5, x plus 1, I want to make sure that both rational expressions have that denominator. So looking at the leftmost one, I notice that what its denominator is missing from the LCD is the x plus 1. So I'll multiply it numerator and denominator by x plus 1. And then the second rational expression, it has the x minus 5 and the x plus 1, but it's missing the x plus 5 from the LCD. So I better multiply it top and bottom by that. And this one has a lot more terms than the last problem, I think, so I better be really careful. I'm just going to rewrite negative 5 times x plus 1. You know what I might do? Sometimes I like to go, well, maybe I'm going to be careful, huh? I don't want to skip too many steps here. All right, we're subtracting what's the second numerator. It was 2 minus x, but I'm multiplying that by x plus 5. And you know what sometimes I like to do? Now that I see that they have the same denominators, you notice they have the same three factors, I just go like LCD, just so I don't have to keep writing it. In the end, when I'm trying to see if it reduces, I'll probably write it out again. But at this point, all the action's happening in the numerator, so I don't really care about the denominator as much. I know that they're the same denominator. I'm going to distribute this negative 5 here, and I'm going to FOIL this out in this numerator. Multiply this whole thing out, because I know that when I subtract these two rational expressions, I'm going to have to combine like terms. So if I distribute the negative 5 in the leftmost one, it'll become negative 5x minus 5. And that's over that LCD. Minus, let's see, if I FOIL that out in the numerator here, that'll become 2x plus 10 minus x squared minus 5x. And that's over that LCD as well. Alright, let's see, now, you know, to me, I don't know if it's really, yeah, alright, never mind. I was going to see if it's worth a step to just combine these two like terms here, but might as well. We got plenty of room, I think. There are no like terms in the numerator of the left rational expression, so I'm going to just rewrite it the same. But the right one, maybe I'll write it in descending order of powers as well. There's a negative x squared that does not have a like term. So yeah, notice that there's a subtraction sign here. X squared itself is negative, so we're going to see two negatives, and they will not cancel yet, since this subtraction sign is meant for everyone in the numerator. And then we have a 2x and a negative 5x. That'll make negative 3x. And then the plus 10 did not have a like term. All right, now I think I'm ready to distribute that subtraction sign onto everyone in the second numerator. So this negative is going to make this negative a positive. The subtraction sign is going to make this negative a positive, and it's going to make this positive a negative. So pretty much everyone's sign is going to change. It was a minus, minus, plus, but now it's a plus, plus, minus. But the same terms, x squared, 3x, 10, over that LCD. There we go. So be careful, yeah, when you see a subtraction sign in front of a fraction, or to the left of a fraction, and the fraction's numerator has more than one term, you better make sure to distribute that subtraction sign onto everyone in the numerator. Alright, what kind of like terms do we have? It looks like x squared does not have a like term, so he's just going to be by himself. But we have negative 5x plus 3x. That'll make minus 2x. And we have negative 15 and negative 10. That's, or sorry, I gave it away, huh? Negative 5 and negative 10 makes negative 15. Alright, that's over the LCD. But now that we want to see if we can reduce, I think I'm going to actually write out that LCD. It used to be I can't remember what order they were in, but it doesn't matter. X minus 5, x plus 5, x plus 1. As long as those three factors are in there, it doesn't matter. And then the numerator, I think, factors into x minus 5, x plus 3. Because those are the two numbers that multiply to negative 15 but add up to negative 2. Negative 5 and 3. And look at this one. It was actually worth trying to reduce because these two factors are the same, so they'll cancel. We're left with just the x plus 3 factor in the numerator, and then the x plus 5 and x plus 1 in the denominator. Beautiful. Alright, I think we're doing good. I think there's another one like this here, number 161. This one looks pretty scary. I think it's actually easier than the last one. It just looks scarier because it has 3 rational expressions. But I think the rational expressions themselves are nicer than the last time. Let's see, just like in the last couple problems, the first thing we're going to want to do is try to factor each denominator to see what the least common denominator is. The first denominator, y plus 2, can't be factored, so I'll just rewrite it. Similarly, the second denominator, y minus 2, can't be factored either. The last one can, though. That's a difference of squares. Y squared minus 4 is y minus 2, y plus 2. But now that I see the factored form of each denominator, I can see the LCD would be made up of y plus 2 and y minus 2. Because those are the only factors I see between all the denominators. And I never see any of those factors more than once here. I see it once here, once there, once here, once there. I don't see 2 in the same denominator or more than 2. So that must be our LCD. So I'm going to multiply each of these rational expressions by whatever it needs to have that denominator, LCD. The leftmost one has a y plus 2, but it's missing the y minus 2. So I'm going to go ahead and give it the y minus 2, numerator and denominator. The middle rational expression has the y minus 2, but it's missing the y plus 2. So I have to multiply that guy. The rightmost one has the y minus 2 and the y plus 2. So I don't need to multiply it by anything. I'm going to leave it the same. Alright, the leftmost one now becomes... I guess I could distribute the 3y, but I'm just going to leave it as is. 3y times y minus 2... And it has that common denominator now. It has the y plus 2 and the y minus 2. Subtract, okay. Second numerator is y times y plus 2. And it now has that LCD. Plus, the very last one already had the LCD. And it stayed the same. Okay. Now, sometimes what's kind of nice is actually, before you even distribute anything, this is an option. It's up to you. You could do it like we did in the previous one where... Like at this stage right here, we distributed the 5 here, and we FOILed this out, and then we combined it into one fraction. Sometimes I think you're less likely to make a mistake if you actually combine these all into one fraction first, and then distribute. Because then I think you won't forget to give this minus to everybody here and all that stuff. This is just an option. You could do it like we did in the last problem, but it's up to you. I prefer this way, actually. Combine into one fraction before distributing. This is optional, but I think it's really nice. So what I mean by that is just, I'm going to write all the numerators over the same LCD exactly as they are. So the first numerator was 3y times y plus, or minus 2. And notice there's a subtraction sign, so there'll be a subtraction sign. The next numerator is y times y plus 2. And then there's a plus sign because we're adding the last rational expression. And the last guy's numerator is just an 8, so there it is. And I think because now they're all together, I don't think I'll have as hard a time remembering to distribute a subtraction sign onto multiple terms and all that type of stuff. Because now, like for example, instead of thinking of this as a y distributing into the y plus 2, think of it as a minus y. And you won't forget to give that minus to everyone. So anyway, I think that's kind of nice. So how about we'll distribute this 3y in here. That'll make it 3y squared minus 6y. And if I distribute this negative y into the y plus 2, negative y times y is negative y squared. Negative y times 2 will be negative 2y. And then we have the plus 8 at the end over that LCD. Okay. Let's see, we got a couple like terms. 3y squared minus y squared makes 2y squared. So those guys are done. Then we have a negative 6y minus 2y that makes negative 8y. And then the only constant term was the 8 that was already there from the beginning. And that's over the LCD. Okay. So now in an attempt to reduce this, I'm going to have to factor the numerator. First thing I notice about the numerator is that everything has a 2 in common. So I'm going to do that first. Take a 2 out. Then I'd be left with y squared minus 4y plus 4. And I think I can factor that further. But now that I'm trying to reduce, I'm going to rewrite the LCD. What was the LCD again? I already forgot. Oh yeah, y plus 2, y minus 2. Oops. Y plus 2. And of course, not necessarily in that order. It doesn't matter. Alright, and then the numerator had the y squared minus 4y plus 4. But that factors into y minus 2, y minus 2. Because those are the two numbers that multiply to 4 but add up to negative 4. Alright, and I'm definitely glad that I factored everything to see if it reduces, because there is something in common. One of the y minus 2's cancels in the numerator and the denominator. But these aren't like terms here, or they're not, you can't cancel a y minus 2 and a y plus 2. So those, they look like they might be cancelable, but they're not. So my answer is left with 2, the y minus 2, and then in the denominator y plus 2. Perfect. Yeah, I don't know if that one was harder than the last one or easier. Seems like it was about the same, huh? Maybe, I don't know. Alright, that was fun. Maybe there are more fun problems. Oh look, there's another one. Wow. How nice. This is from the next section though. So section 6.5, this has the, what are they called? The complex fractions or complex rational expressions, where you have a fraction within a fraction. So these ones you have a choice of how to do these. You could just, for example, take in this big numerator, the 1 over z and the 1, try to get a common denominator between them, combine them into one fraction, and then try to do the same on the bottom, this 1 over z squared and the minus 1. But I think the easier way, it's harder to remember how to do it or what to do, but it's faster and easier, is you just think of what is the least common denominator of all denominators. There's only two denominators here. There's a z and a z squared. Between z and z squared, the LCD is z squared. Alright, and once you decide what the LCD is, you just multiply the entire big numerator by it. So z squared times 1 over z, z squared times 1, and you multiply the entire big denominator by it. Z squared times 1 over z, z squared times minus 1. And that should eradicate any denominators you had, which is nice. So you're using an LCD, but you're not really using it so you can get a common denominator. You're using it to get rid of all denominators. See, so if you want to be really careful, you can put the z squared over 1 and multiply across. So when I multiply z squared over 1 times 1 over z, I get z squared over z, which will reduce in the next step. And then I'm multiplying z squared times 1 in the next term there. That'll just be a z squared. Nothing to reduce there because it's not a fraction. And in the denominator I have z squared over 1 times 1 over z squared. If I multiply across, I get z squared over z squared. And then minus z squared times 1 is z squared. And don't try to reduce right now. You can't reduce yet. You can only reduce if you factored. And we haven't factored yet, so even though these z squareds kind of look tempting to reduce, the only thing I can reduce is within these little fractions here. So let's see, in the numerator we have a z squared over z, that's a z, plus the z squared that was on the right there. In the denominator we have a z squared over z squared, that's a 1, and then minus the z squared that was already there. Alright, so now it's a pretty simplified complex fraction, but I would like to see if it reduces. In order to see if it reduces, I need to factor numerator and denominator. Just remember, you can't cancel these until you factor. Can't cancel, even though I want to. You can't cancel individual terms, even though it's tempting sometimes. You want to factor instead. In the numerator, the z and the z squared have a z in common. I'm going to take that out. See, if a z comes out, what's left? 1 plus z. Alright, and the denominator, 1 minus z squared, that's a difference of squares. So we can factor into 1 minus z, 1 plus z. And what do you know? 1 plus z's are the same, so they can cancel. All that's left is z over 1 minus z. Perfect. I like that. I like when a plan comes together like that. That's nice. Alright, next one should theoretically be similar. I like that method of just taking the whole thing and finding the LCD of all the denominators, multiplying all the denominators by it, you know. So if I look at all these little denominators, there's a D, there's a C, there's a C, there's a D. The LCD would have a combination of those two, CD. So I'm going to do like we did in the last one and multiply CD by both terms in the numerator and then both terms in the denominator. So it'll be CD times the numerator, both terms, CD times the denominator, both terms. And just to be careful if you want, again, to put that over 1 so you know exactly what's being multiplied by what. So when I multiply across, first I'm multiplying in the numerator CD times C over D. So you'll have CD times C in the numerator, that's C squared D over 1 times D, which is D. And then for the second term, you're multiplying CD over 1 times negative, okay, so it's going to be a negative, D over C. The numerator is CD times D, that's CD squared, over 1 times C is C. And then in the denominator, we have first CD over 1 times 1 over C. That'll make CD over C plus. The second term, I'm multiplying CD over 1 times 1 over D. That'll be CD over D. Alright, and each of these fractions should reduce down to something that's not a fraction. So for example, on the top left, the D's cancel, so that term's just left with a C squared. And I guess the top right term, the C's cancel, that's just left with a minus D squared. See, in the bottom left, the C's cancel, just leaving D. And on the bottom right, the D's cancel, just leaving C, plus C. Okay, so there are no more fractions left. That means we've simplified the complex fraction, but we want to see if it reduces. I'm going to see what I can factor here. The numerator is a difference of squares. That's C minus D, C plus D. The denominator D plus C is not really factorable, so I'll just leave it. And at first it looks like, wait, these aren't really the same. There are no like factors, but if you just rearrange these terms, because D plus C, if you switch them, it's the same as C plus D. So maybe I'll rewrite that guy, keeping the numerator the same. Or if you wanted to, you could have switched these two. Instead of C plus D, you could have written D plus C to make it the same as the denominator. Either way, C plus D cancel, and you're just left with C minus D on top. I guess you could say 1 on the bottom, but we know that any fraction over 1 is just that thing, as kind of like a whole number, so we don't need that 1 anymore. The answer is just C minus D. It's hard to believe that that terrible problem just ends up being nice and pretty like C minus D. Alright. That was fun. Let's see what else we have here. Alright, more from chapter 6. I think these are more fun though, because you're actually solving an equation. I just feel like I'm doing more when I'm solving an equation for some reason. Alright, but actually these ones, to solve these equations, you kind of have the same idea we did in the previous problems, where you're going to find the least common denominator, but you're not going to use it to actually get everyone to have the same denominator. You're using the least common denominator to clear all denominators. So for each of these problems, I'm going to first think about what the LCD will be. If I have to factor a denominator to figure it out, I will, but for example, in this problem, 164, there's only 3 denominators and they're simple, x, 4, and 2. So there's no really need to factor. Looking at all those guys though, I know the number-wise, the LCD would be a 4, because that's the largest, I guess the largest number that they all divide into, or sorry, smallest number they all divide into. But then also there's a variable in a denominator, x, so I need that as part of my LCD. Alright, and if you want, you don't have to write that out, you can just kind of keep that in your head. Just say, oh, the LCD is going to be 4x. So we're going to take that LCD 4x and multiply the entire equation by it. So 4x times the first fraction times the second fraction, and times the third. And maybe to be careful, like in the previous problems, I'm going to put that 4x over 1, just so I can see exactly what's going on there. So multiplying across, I have first 4x over 1 times 3 over x. That'll become 12x over 1 times x is just x. And then for the second fraction, I'm multiplying 4x over 1 times negative 1 over 4. That's going to be a negative 4x over 4. And then on the other side of the equation, I'm multiplying 4x over 1 times 1 over 2. That'll become 4x over 2. See, all right, and each of those should reduce. The first fraction just becomes a 12 since the x's cancel, minus the second fraction, the 4's cancel, so you're left with x, and then equals, the very rightmost fraction reduces as 2 goes into 4 twice. So there you're left with a 2x. And now this equation is really simple to solve. I almost don't believe my luck right now. I'm going to get the x's together by maybe moving this x to the right side. That way 12 is all by itself. It's equal to 3x. And my last step will just be to divide by 3. There we go. X must be 4. Beautiful. Alright, and at this stage you're supposed to check to make sure that this value that I got as a solution won't make any denominator 0. Yeah, let's see. Will this value cause any denominator to be 0 when substituted? And you can just kind of check that in your head. Just go back to the original problem and say, all right, where are all the denominators? Here's a denominator of x, here's a denominator of 4, here's a denominator of 2. There's only one x, so there's only one place to put this value here. And then it would be 3 over 4. That's not a problem. It's only if there's a 0 in the denominator. So like, let's say in the end we ended up with 0 as a solution. That would be a problem because if I substitute 0 in, it'll be 3 over 0. And that's what we're trying to avoid. In that case, we'd have to throw that answer away and say there's no solution. So you should check this in your head, kind of. You don't have to maybe necessarily say this out loud or write it out loud, but that should be a little mental check at the end of these problems. Okay, let's try this next one. Now that we kind of got an idea. Looking at this problem 165, I'm supposed to find the LCD, but there's only one denominator, so he must be the LCD x. Just like in the last one, I'm going to multiply the entire thing by that LCD. Every term, so even the ones that aren't fractions. I've seen that mistake made a lot of times is people doing these problems, they remember to multiply by the LCD, but they don't remember that you have to multiply every single term by that LCD. No matter if it's a fraction or a whole number or a variable. It's only, I guess this is only a valid move if everybody gets that LCD. So since there are 3 terms in this entire equation, all 3 get multiplied by x. Alright, so first we have x times x, that's going to be x squared, plus, but then x times 6 over x, I might put this x over 1 just to think about how that's going to work and multiply across. 6 times x over 1 times x. And then on the other side we're just doing x times negative 7, that'll be negative 7x. Okay, so I can't really do much with this term, x squared, but the second term is just 6 since the x's cancel. And then equals nothing much to do with this negative 7x. But now that I see this equation is fairly complicated because, unlike the last one, I have an x squared and an x term. So it's not just really easy enough to isolate x like in the last problem. I have to get all the terms on one side and try to factor this thing. So I'm going to move the 7x over, write these in descending order of powers, x squared plus 7x plus 6, and then try to factor this guy. So should factor, I've got x and x. What multiplies to 6 but adds up to 7? Well, 6 and 1, or 1 and 6, either way. And now that I've set each factor equal to 0, now that I've factored it, I'm going to set each factor equal to 0. X plus 6 equals 0, x plus 1 equals 0. And if I solve each of these individually, this guy by subtracting 6, I got negative 6 as one solution, And let's see what the other one will be. If I subtract the 1 to the other side, looks like -1 is the other solution. But I should check this, what we wrote over here. So yeah, we should check what we wrote in here. Will either of these make a denominator 0? If we look back at the original problem, there's only one denominator of x. So imagine if the first solution was the case, x equals -6. If I put a -6 there, well, then the denominator is just -6. It's not going to be 0, so that's fine. And then similarly with the second answer we got, -1. If I put a -1 in that denominator, it's just going to be a -1, not 0. So both answers are fine, so I'm going to keep both. Alright, the last problem in this section, oops, it looks similar, so hopefully it'll go smoothly. But I think because there's two denominators and they're both fairly complicated, the LCD will be more complicated. So we have the first denominator has an x minus 1. I mean, you would try to factor these denominators if you could, but they can't be factored. So I need each one of those x minus 1 and one x plus 1 in my LCD. So unfortunately, that's what I'm going to have to do, is take x minus 1, x plus 2, and multiply that entire thing by every term in this equation. Don't miss the 1. He's a term as well. Okay. So if I multiply the whole LCD x minus 1, x plus 2 by the 1 first, it'll just be that thing, x minus 1, x plus 2, since multiplying by 1 doesn't change something. But on the other side of the equal sign, we have a bunch of fractions, so I'm going to put this thing over 1 and multiply across. First, it's x minus 1, x plus 2 times 2. You could put the 2 on either side, but for some reason 2 on the left side looks more correct to me. And the denominator we're multiplying 1 times x minus 1. It'll just be x minus 1. Alright, then the very last fraction, 2 over x plus 2, gets multiplied by that x minus 1, x plus 2. The 2 that was already in the numerator times the x minus 1, x plus 2, over, the denominators are 1 times x plus 2. That'll become x plus 2. Or, remain x plus 2, I guess I should say. Alright, and the whole point of that, remember, the whole point is that once you multiply the LCD, there should be no more denominators once you reduce. So for example, here x minus 1's cancel, here x plus 2's cancel. So you should be getting rid of denominators right now. On the left side, there was never a denominator, so we don't need to worry about it. It'll just be the x minus 1, x plus 2. On the right side, 2 and x plus 2 are left from that first term, and then plus the 2 and the x minus 1 are left from the second term. Alright, now to solve this, having all these parentheses and things stuck inside parentheses isn't really helping. I'm going to have to undo all these parentheses by foiling and distributing stuff. Great. Okay, so I'm going to FOIL this out here, and then distribute this 2 here, distribute this 2 here. And we'll see what kind of shenanigans we get into after that. If I FOIL the left side, it'll become x squared plus 2x minus 1x, or x, minus 2. On the right side, if I distribute the first 2, I get 2x plus 4. If I distribute the second 2, I get 2x minus 2. Okay, let's combine some like terms here. On the left side of the equal sign, there are 2 like terms. 2x minus x makes x. Alright, that's about it. And on the right side, you have a 2x and another 2x makes 4x. The 4 and the negative 2 make 2. And now that I see what I have, I see x's and I see an x squared. So it won't be enough to isolate x, since there's an x squared term and an x. I'm going to have to get everything on one side and factor. And I think it'll be easier to move this 4x to the left as well as this 2. And that's because I don't want to move the x squared to the right side. If I move the x squared to the right side, it'll become negative, and it's going to be harder to factor that way. So I'll be left with x squared. The next term we had an x, and we're subtracting 4x. That'll become minus 3x. And then negative 2 and negative 2 make negative 4. Okay, now let me factor this guy. He factors into x minus 4, x plus 1. because those are the numbers that multiply to -4 and add up to -3. And now I'll set each of these factors equal to 0, and that should give me my two potential solutions. So if I solve the first guy, I'll be adding 4 to both sides. That'll give me 4. If I solve the second guy, I'll be subtracting 1 from both sides, and that'll give me -1. Those should be my two solutions. I should just do a little mental check to see if either of those would give me a 0 denominator. So think about 4, for example. 4, there would be no problem with 4 for sure. So what if you put a 4 here in this x? 4 minus 1 is 3. That's not 0. That's only if you get a 0. If I put it in the second denominator, 4 plus 2 is 6. That's not 0. So 4 can stay. I'm actually, 1 kind of scared me, or -1 kind of scared me. Because I thought, oh, what if I put a -1 in this denominator? But think about it, it's -1 minus 1, which is -2. That's not 0. And if you put -1 in the second denominator, -1 plus 2 is +1. So no matter what, you're not getting a 0 denominator, so I can keep both solutions. Yeah, but if either of those produced a 0 denominator, I have to throw that solution away. I would only have the other one left over. Okay. Almost at the end of this chapter 6 stuff. This was probably the most difficult part of this chapter, I think. Because of course it's applications. Let's see, but we keep coming back to these distance, rate, time problems. They should be sort of familiar by now, since we've seen them so many times. Remember how it goes? You're going to have this little table of values. You're going to label the two rows as whatever parts of the trip they're talking about. In this problem, it sounds like they're talking about a boat traveling downstream and a boat traveling upstream. So I think that's how I'll label these guys. Downstream, upstream, or vice versa. It doesn't matter what order they're in. And then there should be one piece of information they just give me right off the bat. Either both distances for the trips, both rates, or both times. They should just give me one of those. So what do they say? This current, okay, the current is 6 miles an hour. That's not really helping me. I mean, that sounds like a rate, but think about, what are they asking for here? What is the speed of the boat in still water? That's what we want. So I'm going to let my variable be that, the speed. Remember, speed is the same as rate, so that r over there is the same as speed of the boat. In still water. Okay, so let's see. Even though they said the Black River's current is 6 miles an hour, you're not going to put a 6 here or here, because think about what's happening here is it's the boat that's traveling. So the speed of the boat is not the same as the speed of the current. The speed of the boat is probably faster than the speed of the current. So 6 will have to do with it, but it's not going to be just 6. Unless we were talking about just the river by itself without the boat. But no, in this problem we care about the boat speed, not the river speed. So the 6 miles an hour, we'll use it, but that's not what they're giving us right off the bat. Okay, it says a boat travels 50 miles downstream. Well, that kind of sounds like something they just gave us. That's a distance for sure. So 50 miles is the distance that they travel downstream. And the same time it takes the boat to travel 30 miles upstream. So that sounds like the distance upstream, 30. Perfect. All right, there's the thing they just give us. And then from there, they said there should be some kind of relationship with, I guess, variable relationship between the rates or the times. One of the things that's left. So notice, though, they did say it travels the same time, it travels the same time downstream and upstream. But I don't know what to put here still. I know that these times will be the same, but what are they? I don't even know what to write there. X and X? I don't think that would be helpful. So those, I think I might have to hold off on that. But I think I can say, let's say if X is the speed of or rate of the boat in still water, how about downstream? Downstream is easier, right? Because the current's kind of helping you. So it would be however fast you would be going normally, the speed of the boat in still water plus 6. That's the rate. So that would be the rate downstream, X plus 6. Upstream, though, you're having a harder time. It's like, okay, if there was no current, I'd be going X miles an hour. But since the current's pushing against me at 6 miles an hour, my new rate is going to be whatever speed I was going normally minus 6. I'm going 6 miles an hour slower because of that current. So yeah, notice the 6, it did end up in our rate, but it wasn't our entire rate. It just kind of had to do with it. So we got distance, we got rate, and then remember the very last thing you're supposed to fill in this case it's time. You're going to find that last thing, or fill this in using the formula, distance equals rate times time. So since the thing that we're trying to kind of fill in right now is time, I want to isolate t in this equation so I can figure out what it is above. To isolate t, I'll divide both sides by r. That way d over r, that must be t. Time is distance over rate. Alright, that's going to help us. So notice, for downstream, for example, if I just focus on the downstream row, the time here is going to be its distance, which is 50, over its rate, which is x plus 6, according to this formula. So the time it took them to go downstream is the distance downstream, which was 50, divided by its rate downstream, x plus 6. And then similarly, for upstream, the time will be its distance, which was 30, over its rate, which was x minus 6. Alright, now that we've filled in the everything in the table, I think the next step, as we outlined, remember we outlined all the steps on how to solve these? The next step was the very last thing you filled in this case time, there should be some kind of spoken or unspoken relationship between those two times. And we actually wrote it here. Remember, the times were the same. Or you could say the times were equal. So I'm going to say, this part you don't have to write out. This is kind of like me brainstorming. The time downstream should be equal to the time upstream. And we filled in the time downstream was that fraction, 50 over x plus 6. The time upstream, we just filled that in the table, 30 over x minus 6. So there's our equation. So let's try to solve this guy. Alright, this is the application of solving rational equations. So we should do like we did in previous problems. I'm going to multiply the whole thing by the LCD. I would try to factor the denominators, but they can't be factored. That's as good as they get. So the LCD here is going to be each of those factors put together, the x plus 6 from this first denominator and the x minus 6 from the second denominator. And there are only two terms here, one on each side, so I only need to multiply once on each term. I'm going to put that over 1 as well, so I kind of know what's multiplied by what. So first it's x plus 6, x minus 6 over 1 times 50 over x plus 6. If I multiply across, I have 50 times the x plus 6, x minus 6, I'm giving that, over 1 times x plus 6, which is just x plus 6. On the other side, if I multiply, I get 30 times the x plus 6, x minus 6 that I'm multiplying by, over 1 times x minus 6 will just be x minus 6. And then all our denominators should disappear now, and they do, because here x plus 6 cancels, here x minus 6 cancels. On the left, all you're left with is 50 times x minus 6. On the right, you're left with 30 times x plus 6. Now I think to solve this, I'm going to have to distribute. So I'm going to distribute this 50 in 50x minus 300. Over here, I'm going to distribute the 30x plus 180. And thankfully, this is better than I thought. There's only an x, there's no x squared term here. So I'm able to just isolate x. I'm going to move this 30x to the left so the x's are together. Maybe while I'm at it, I'll add the 300 to the right. That way x's are on one side and numbers are on the other. So on the left we have 50x minus 30x, that makes 20x. The 300s are gone because we moved it. Equals 180 plus 300 is 480. And then the last step would just be to get rid of that 20 by dividing by it. And that's it. X is, that would be 24? Yeah, 24. And I think in the problem we actually wrote it out. We said let x be the speed of the boat in still water. And they were talking about miles per hour. So it must be that the speed of the boat in still water is 24 miles per hour. Nice. Alright, so those problems are pretty difficult, but the more of them you practice, the better you'll get at them. Yeah, I would definitely try to maybe go over the ones we did in the notes from this section. Try to do them on your own, and then if you need more, maybe go to the homework website and try to do the ones from the study guide. Yeah, there should be an option on the left for study guide, and then you can choose the section and just practice a bunch of problems from there. That should be helpful. And then I think chapter 10 just seems like, after chapter 6 it seems so easy. Even though it's not really easy, just in comparison it seems like it. Let's see, this first problem is just the square root of 100 over the square root of 121. Yeah, I think if you have a fraction inside a root, it's just best to split it up into two roots. 100 gets its own root, 121 gets its own root. Then I can just say, oh, the square root of 100 is 10, the square root of 121 is 11, and that's it. For the next problem, notice that the next one and the next one, number 169 and 170, they're almost the same. It's just the placement of the negative. Remember, when the negative's outside, that's fine. It's just going to carry into your answer. So my answer here is going to be negative whatever the square root of 25 is, and that happens to be 5. But in the next problem, since the negative's inside the root, that's going to be an imaginary answer. But at this point, we know about imaginary numbers, so they're going to expect us to write. Remember that what happens is you take the negative away and put an I there instead. So this is now the square root of 25 with an I. And then if that doesn't sound familiar, you should go back and review section 10.1. That's how you kind of rewrite any imaginary number as something in terms of I. And now that it's just the square root of 25 with no negative, I know what that is. That's 5. So your answer there would be 5i. Definitely two different answers, even though they both look the same. Depends where the negative is, inside or outside the root. And then number 171, here notice it's a cube root, so it's different. We're not asking now what multiplied by itself twice is 64. You might think 8, because 8 times 8 is 64. This is asking what number to the third power is 64. So what times itself 3 times is 64, not twice. That answer would actually be 4, since 4 to the third power, 4 times 4 times 4 is 64. So be really careful, that little index is 3. That really matters. We didn't see any indexes of anything but 2 until now at this point. It's kind of similar. We got number 172 here. The fourth root of 81, this is saying what number to the fourth power is 81. And if you want, you could just start guessing. How about 1 to the fourth? 1 times 1 times 1 times 1 is 1? No, that's not right. I want 81. How about 2 to the fourth? 2 times 2 times 2 times 2 is 16. That's not right either. Keep going until you get 81. 3 times 3 times 3 times 3. That happens to be 81, so that must be the guy. 3 is our answer. Anyway, so don't feel like you have to memorize all these guys. You can just kind of start guessing. All right, well, I need something that raised to the fourth power gives me this thing, so what would it be? And now the last one in this section, 173, you notice that, okay, the index is 5, which is an odd number. So it's okay to have a negative inside the root. It's only when you have an even index, like 2, 4, 6, that's when the answer is going to be imaginary. This should actually have a real answer. So this is asking, what can you raise to the fifth power and get negative 32? I mean, you can start guessing stuff if you want. Well, for sure I know the answer is going to be negative. Because how can a positive number to the fifth power be negative 32? That wouldn't make sense. Negative, and if you just try 2, that works. 2 times itself 5 times is 32. 2 to the fifth, 2 times 2 times 2 times 2 times 2 is 32. So the answer to that one would be negative 2. Alright, so those problems are kind of a good warm-up for the rest of the ones in this chapter here. So section 10.2, this stuff is saying they just want you to write an equivalent expression using exponential notation. So for example, in number 174, we're not really trying to see what the cube root of 5ab is to the fourth power. All they want us to do is rewrite it. We're not really trying to, I don't know, figure out what it is like in the previous problems. So what they want us to do, I think, is just say, all right, this whole thing, 5ab, has a cube root. And remember, if you're wanting to write this as a rational exponent, the type of root, which is a 3, index of 3, that'll become the denominator of the exponent. So it'll be 5ab to the something over 3 power. And if there's an exponent outside, that's going to be the numerator. So it's 4/3 power. Yeah, remember that the index of the root is the denominator of the exponent. And then the power is going to become the numerator of the exponent. It's kind of how you know what goes where. That's all they wanted. This is all they want. Oops, shoot. This guy. 5ab to the 4/3 power. That's it. Easy peasy. Seems kind of pointless, but I think they just want us to remember how to rewrite it, you know? Like, oh, the 3 is the index. Is that the numerator or the denominator? I forgot. And kind of similar for number 175, except now it's kind of backwards. We have something to the 1/5 power. Remember what we said down here. The denominator of the exponent, which ours is 5, that'll become the index of the root. So it must be a 5th root of all the stuff that was inside the parentheses, 3w squared. And since the numerator was just a 1, we could put a 1, this all to the 1 power, because of that guy. But anything to the 1 power is that thing, so you don't really need that 1 power. It'd only be if that was anything but a 1, like a 2, 3, 4, 5. Okay. Now number 176 is saying, simplify using rational exponents. Okay. So kind of a similar thing. They're saying, basically, if it had a root, write it as an exponent. If it had an exponent, write it as a root. But part A and part B, we have a root. So really, they just want us to write this as a power. This is x to the some kind of fraction power. But remember, we said the index is going to be the denominator. And the exponent, or the power, is going to be the numerator. That's what we wrote over here, right? Yeah. Index of the root becomes the denominator, the power becomes the numerator. Okay. The index of the root is 12, that's the denominator, the power is 9. And that's just a fraction 9/12. I know how that reduces. 9 over 12 reduces to 3/4. Okay, now that we've reduced it, I think they probably want us to write this back as a root. So I'm going to say, all right, remember the denominator is the index of the power, or sorry, the index, 4th, so it's a 4th root, and then the numerator is the power. This guy's the index, this guy's the power, yeah. And that's it. Okay. So next one, notice there's a power here outside, 2. So I know when I write something to the fraction power, the numerator is going to be 2, because we said the power is always the numerator. And then notice the index is 6. That's going to be the denominator. And what's being raised to that power is just everything that was inside the root, x squared y. And of course, that fraction 2/6 reduces to 1/3. And now that I've reduced the fraction, I say, okay, what does a 1/3 power mean? The denominator is 3. Remember, the denominator becomes the index of the root. So it's a cube root of all the stuff that was inside the parentheses. And I could say that's all to the 1 power because of the 1 here, but anything to the 1 power is that thing. So I'd be kind of silly to write the 1. Unless it was something other than 1, then I would write it. Alright, this is fun. Let's try the next one. Number 177. Okay. We got a square root of 49x to the 4th. I think when we tackle these problems in the notes, I said, you know what I like to do? When it's something, 2 things multiplied inside the root, I split it into 2 separate things. Like 49 gets its own root, x to the 4th gets its own root. 49 square root of 7. The square root of x to the 4th, if you remember, you could do this the tricky way where we say, remember, you take the index, which is, it's a square root, so it's a 2, divide the index into the power, and that'll be the resulting exponent on x. the index 2 goes into the power 4 twice. It'll be 7x squared. 4 divided by 2 is 2. Man, that's really it. And I remember before, like I think in this section we were really worried about absolute values and stuff, like, oh, would this be 7 absolute value x squared or not? But I think later on they said, oh, you know how we worried about absolute values a lot? Don't worry about them anymore. So pretty much on the final exam, don't even worry about any absolute values. It's not important anymore. I mean, I guess you should know in the back of your mind that they exist, and they should be there, but they're just so complicated, we kind of just say, meh, don't worry about it, guys. Too complicated, too silly. That's one less thing to worry about, at least. All right, let's try 178. We're going to go sort of a similar approach. Anything that's being multiplied inside the root, I'm going to split it up and give it its own root. So the 16, for example, can have his own fourth root. The x to the 20th can have his own fourth root. And then the y to the 8th can have his own. So fourth root of 16 is 2. Because that's asking what times itself 4 times is 16. Well, 2 times 2 times 2 times 2 is 16. And then to simplify the x to the powers, we're going to do like we said in the last problem. We're going to divide the power, for example 20, by the index 4. 20 goes into 4 5 times, so this will become x to the 5th. And then the same thing for y. I'm going to divide the index 4 into the power 8. 4 goes into 8 twice, so that'll become a y squared. And that's it. 2. They don't have to be all separate like that. You could just write 2x to the 5th y squared. You know. That's it. Beautiful. Next one. All right. 179. This is getting more complicated because I think 250 doesn't have a perfect square root. So we'll have to simplify it and stuff. And then x to the 3rd doesn't have a square root either. We'll have to simplify it. And my first step's going to be the same. I'm going to give 250 his own root. Give the x to the 3rd his own root, and the y squared his own root. So 250 doesn't have a square root. I think what we did was we said, all right, I'm going to take 250 and prime factor it. 250 is what times what? I mean, you could start out with anything. Whenever anything ends in a 0, I always think 10 times, for example, 25. That makes 250. 10 is 2 times 5. Okay, and both of those are prime, so I'm going to circle them. 25 is 5 times 5, and both of those are prime. Okay. So since this is a square root, the index is 2. I'm looking at the prime factors, and I want a group of 2 of the same ones. I see that there's a group of 2 5s there. But the 2 and the 5 that are left over, those are different. They're not the same prime. So those both will be stuck inside the root, unfortunately. But since there's one pair of 5s, a 5 will get to escape the root. But that 2 and that 5 that did not have a pair, they have to stay inside. Alright, so that's good for the numbers. How for the x to the 3rd? So this is where we do a similar thing. I'm going to divide the index into the power. Dividing the power 3 by 2. Well, 2 doesn't go into 3 evenly, but it goes in once with the remainder of 1. That means there's going to be 1x outside and 1x inside. Remember, the number of times it goes in is how many get to escape. The remainder is how many have to stay in. Remember, the remainder is how many have to remain. That's how I kind of remember it. And then same for the y. The index is 2, so I'm dividing the power 2 by 2. It goes in evenly, so just be y to the 1. No remainder, so there's no need for a y inside the root. All right, then we want to just gather everything that was outside the root, which we had a 5 and an x. This guy escaped. And then the y. They're on the left, and then anything that was kind of stuck inside the root, I'm going to put them together. 2 times 5 times x is 10x. Beautiful. Okay. This problem, it looks kind of like, okay, what the heck am I supposed to do with this? The square root of 5a times the square root of 7b. If we look at each root separately, for example, the square root of 5a, I can't simplify that because even if I try to split it, the square root of 5, the square root of a, there is no square root of 5. Nothing divides into 5 that has a square root, so it can't be simplified. And the square root of a can't be simplified because if I tried to, I would divide the index 2 into the power 1, but 2 can't go into 1. So it'd be there's no way to simplify the first root, there's no way to simplify the second root. The only thing I can really do is multiply. And the rule for multiplying radicals is, as long as they have the same index, you're okay to multiply them. These both have an index of 2, so it's okay to multiply. 5a times 7b is 35ab. And that's all they want, really, because you can't simplify that for the same reasons we talked about. The same reasons the first root couldn't simplify. And that's it. Alright, and similar for the second one here. Looking at this first root in number 181, the cube root of 3, there is no cube root of 3, and that's too small to simplify. And then 9 as well, so I think what I'll do is probably multiply across and then try to simplify if possible. I mean, if these were bigger numbers and more, I don't know, like if the numbers 3 and 9 were larger and they could actually be simplified, the cube root of those things actually had cube roots, then I would probably try, but this one, that's not really worth it. I'm going to multiply across. And they both have cube roots, so we're okay to multiply. So 3 times the 9, that makes 27. X to the 4th times x to the 1, you add the powers. 4 plus 1 is 5. Same with the b's. You have a 1 power here and a 2 power here. That adds up to 3. Okay. Fly insides. Alright, now I'm going to give each of those things their own root. The 27 gets its own root. The x to the 5th, the b to the 3rd. Okay, the good news is 27 has a cube root. It's 3. Since 3 times itself, 3 times is 27. So for the x, I'm going to have to do my little trick there. Try to divide the index into the power. Oops. Index 3 into the power of 5. How many times can 3 go into 5? Only once, with 2 remaining. That means 1x got to escape, but 2 x's have to remain inside. Alright. And then the b's, you could do the same division, or you could just say, well, a cube root and a cube cancel, so it's just b. Or you could actually divide the index into the power. 3 goes into 3 once, evenly, so there's 1 b with no remainder. And this is a good answer, but you'll see them, they always bring everything outside the root on the left, and then anything inside the root on the right. So you definitely see them write it like this, with the b next to the other guys. Alright, I think the most complicated one now. You got a cube root of negative 24, x to the 10th, y to the 8th. Man, and 24 is a fairly large number. I think it can be broken down quite a bit. Same thing with 18 over here. It's like this one, maybe unlike the last one, it might be worth trying to reduce either of these separately and then try to multiply them. I mean, you could multiply them first, but imagine, what's 24 times 18? Well, that's going to be a huge number, and it's going to be harder to try to reduce that guy or see what its cube root is rather than these two separate smaller numbers. So I'm going to look at 24. Try to prime factor it. 24 can be 2 times 12. 12 is 2 times 6. And 6 is 2 times 3. Since the index is 3, I need a group of 3 primes to escape. And I do see a group of 3 2's here. 2, 2, 2. So that means 1 2 gets to escape. You know what I should do? I forgot. I should go give the 24 its own cube root, the 10 its own cube root, and the y its own cube root. Okay, now we're going to keep going. I'll worry about this guy later. Let's see. And it's negative, so the negative's going to escape 2, because we said 2 times 2 times 2, there's 3 2's, so a 2 gets to escape. But there's one odd man out. This 3 has to stay inside, because he doesn't have a couple of 3's to escape with. As far as the x goes, I'm going to divide its index into its power. Its power is 10, and its index is 3. So we're dividing 3 into 10. 3 goes into 10 3 times, with 1 left over. So that means 3x has got to escape, but 1x has to be stuck inside. And as far as the y's go, that's the cube root of y to the 8th. So I'm going to divide the index into the power. 3 into 8. 3 can go into 8 twice, with 2 left over. That means 2 y's got to escape. Since the remainder was 2, 2 y's remain inside. Now I do the same thing to this cube root of 18, x to the 7th, y to the 4th. But before I do, I might clean this up a little bit. I'm going to take everything that's outside the root and throw it on the left. Negative 2 is outside the root, x to the 3rd is outside the root, and y squared is outside the root. And what's stuck inside the root? The 3, the x, and the y squared. There we go, and that'll be easier to multiply by whatever I get from this other part. Okay. I'm going to give the 18 his own cube root, the x to the 7th his own cube root, and the y to the 4th his own cube root. So 18, I know it doesn't have a cube root exactly, but let me kind of try to break it down. 18 is 2 times 9, and 9 is 3 times 3. Oh, but notice since the index is 3, I would need a group of 3 of the same prime in order to reduce this guy, but I don't see 3 of the same prime. I see 2 of the same prime. Alright, but unfortunately 18 can't be simplified inside a cube root, so I'll just have to leave it. Oh well. Maybe when I multiply everything together, all the blue and the red, then I'll be able to simplify more. So cube root of x to the 7th, I'm going to divide the index into the power. 3 into 7 goes in twice with 1 left over. That means that 2 x's get to escape, but 1 has to remain inside. As far as the y's go, I'm dividing the index 3 into the power of 4. 3 can go into 4 once, with 1 left over. That means 1 y got to escape, and 1 y has to remain inside. Alright, let me gather everything that was outside the root. The only thing that got to escape from the root was the x squared and y. But the stuff that had to remain was 18, x, and y. Okay, now we'll multiply these guys together. So kind of, it's like you're multiplying like terms, sort of. So the negative 2 out front, there's no really number out front to multiply him by. So he'll stay the same. Negative 2 times, I guess, like 1. It'll just be negative 2. The x's, I'm going to multiply them together, the ones that are outside. X to the 3rd times x squared. If I add their powers, I get x to the 5th. The y's, you add y to the 2nd times y. If you add their powers, 2 and 1 make 3. Now we're on to the roots. What's inside the root here? 3 and 18 here. 3 times 18 is 54? Yeah, 54. And then the x's, x to the 1 times x to the 1. You add the powers and get x to the 2nd. The y's, you have y squared times y to the 1. If you add their powers, you get y to the 3rd. Alright, beautiful. Now, unfortunately, it could be that this, what's in the root now, that it's kind of bigger because we multiplied, it could be simplified. So let's see, I'm going to split it up into a few pieces. Give the 54 his own cube root, the x squared his own cube root, and the y cubed his own cube root. So let me try to prime factor 54. 54, I mean, you can prime factor it any way you think of, but I think of 2 times 27. 27 is 3 times 9, and 9 is 3 times 3. This is a cube root, so I need a group of 3 of the same prime, and I do see 3 of the same prime here. There's a group of 3 3's, so 1 3 gets to escape, but there's a 2 that's all by himself here, so 1 2 has to stay inside the root. To simplify the cube root of x squared, I would try to divide the index into the power. 3 index into power 2, but 3 can't go into 2. 3 is too big to go into 2. So unfortunately, the x squared can't be simplified inside the root. It has to stay. But the y can, because notice you're dividing the index into the power. 3 into 3 goes in exactly evenly once. So 1 y gets to escape and no y's are stuck inside the root. And all the stuff that was in front is carried along. Okay. But now that there's more that escaped, I'm going to kind of multiply everything that's kind of like terms. A negative 2 was outside, but a 3 popped up outside as well. Negative 2 times 3 is negative 6. And then I have an x to the 5th outside. No other x's escaped, so he's all by himself. The y to the 3rd and this new y that popped out multiply to make y to the 4th. And the only things left in the root are the 2 and the x squared here. Whew! That's about as bad as these problems get, I think. That was pretty bad. As long as you take your time and don't try to rush through it, you should be okay. Yeah, look how many steps we took, huh? 1, 2, 3, 4, 5, 6, 7 steps. And that's not even mentioning all the side work over here. Ugh. Good times. If you can do a problem like that, you know you're gonna, oh man, you know exactly what you're doing. You're gonna kick some booty. Okay, next section. Ooh. Ooh. All right, that's enough of that. You got a cube root over a cube root. I think either of these cube roots, there's not much to do with them. Like, for example, 60 on top. If I try to prime factor him, what's 60? 10 times 6. 10 is 2 times 5. 6 is 2 times 3. But this is a cube root, so I need 3 of the same prime in order to try to reduce this. And there's no 3 of the same prime, so that wouldn't really help. I think really what I want to do is try to combine this into one root and then reduce. So you're free to do that, yeah. If you have a fraction under a root, you can split it into 2 roots, or if it's split into 2 roots to begin with, you can combine them into one root. That's as long as they have the same index, and these do, they're both cube roots. And then I'll just reduce that like a regular fraction. 60 over 10 is 6. The x's just cancel outright, and y cubed is left. So that simplified quite a bit. The cube root of 6, I don't think there's much I can do with him, but the cube root of y cubed, there might be something I can do with that. If you divide the index into the power, it goes in evenly once, so this just becomes y. There is no cube root of 6, so you just have to stay the same. And 6 doesn't break down anymore, so you could write cube root of 6 and then y, or y and then cube root of 6. Doesn't really matter. I know it kind of depends on preference. If you like the number before the variable, this is probably what you like. But a lot of times we like to see the thing that's outside the root on the left and the thing that's inside the root on the right, no matter what's a number and what's a variable. But either one doesn't really matter. They're both good. All right, now what? Next one, simplify. All right, this one, what are we going to do? You know, this one we could do something similar if we want to. We could say, well, yeah. Well, notice this 2 is outside the root, so he's not going to be involved. It's going to be almost like, since the 2's in the denominator, you're going to kind of pull it out so it's a 1/2. And then the 75x was inside the root, so was the 3. So they can be combined into 1. Yeah. Or you could have written it like that whole thing inside 1 root and then over 2, since 2 is in the denominator. Either way. But let's see, the 3 goes into the 75 25 times. This guy reduces to 25x and it's over 2. Or you could have the 1/2 outside still. But either way, so be careful, this is not 5x over 2. Why? Because you're taking a square root of 25 and you're taking a square root of x. Yeah, the square root of 25 is 5, but the square root of x is not x. That's why I really like to split it up when you see a number and a variable. Give them each their own root so you don't mess it up like that. 25 does have a square root of 5, but x doesn't have a square root. Because again, you'd be trying to divide the power 1 by 2, the index, and it's not going in evenly. So be careful, yeah. The square root of 25x is not 5x. It's 5 square root of x. So be careful on that. Even though part of it can escape the root, that doesn't mean everything gets to. The x did not get to escape, only the 5. Let's try this problem, number 185. Okay. We've got a 4th root of, let's see, we got 48, a to the 11th, c to the 8th. There's nothing really to combine here, like in the previous problem. I don't have any like terms. So I think what I'll do, I'm going to see if I can simplify this. But just like before, I'm going to give everybody their own root. The 48 can have his own. The a to the 11th can have his own. Even the c to the 8th can have his own. It's just he's in the denominator, but that's okay. So, okay, the 48, I'm going to try to see if he can break down. 48 is what times what? Maybe 2 times 24. 24 is 2 times 12. 12 is 2 times 6. Oh my gosh. 6 is 2 times 3. Since this is a 4th root, the index is 4. I need a group of 4 primes to escape, and I just happen to have exactly that. So that means that this 4th root of 48 becomes 2, because a 2 got to escape since there was a group of 4. But then there's one guy left out. He has to stay inside the 4th root, the 3. All right, so that's good for the number. How about the a? We're going to use our trick where we divide the index into the power. So the index is 4. I'm dividing it into the power of a, which is 11. 4 goes into 11 only twice, with 3 remaining. That means, okay, 2 a's get to escape, but 3 have to remain inside the root. 4th root of a to the 3rd. And then the c, if I divide the index into the power for c, I'm dividing 4 into 8. 4 goes into 8 twice, with none left over. That means 2 c's got to escape and no c's had to stay inside the root. And that looks good. I think the only thing left to do maybe is gather the things that were outside the root, like the 2 and the a squared. And then anything that was stuck inside the root, you might as well put them together, 3 and a cubed. That's really all there is to do, yeah. I think that looks good. Okay, oops. What do we got? All right, rationalize the denominator. This one, you've seen it before, but it's easy to forget how to do it. All right, so for simple ones like this guy, number 186, the denominator just contains a square root of 2. So really all we have to do is, remember, rationalize the denominator. That means we want to rewrite this as an equivalent expression, but we don't want to see a root in the denominator. So all I need to do is multiply this guy top and bottom by that root, and it'll magically disappear. This is probably something I would write on my note card for the final, you know? Write out, okay, to rationalize the denominator, you do blah, 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 blah. And in other cases, we'll see more complicated ones where we'll have to do something else. So you might want to, on your note card, differentiate between the different types of problems. But anyway, for this guy, it's just 1 square root on the denominator. So you multiply numerator and denominator by that root. The numerator had a 7. It was not in the root. This 2 is in the root. They can't really interact. They just kind of sit next to each other. But in the denominator, it's a root times a root, so we can multiply them together. 2 times 2 is 4, or you could write 2 squared, which I think we did in the notes to get ready for the harder problems. And a square root and a square cancel, remember. As long as the index and the power match, they cancel. So you're left with 7 square root of 2 on top over 2 on the bottom, because the root disappeared with the square. So that, if you put that in your calculator, 7 root 2 over 2, that's the exact same thing as what we started with. You're going to get the exact same value as if you put 7 divided by the root 2 in your calculator. It just looks different, and they don't like seeing roots in the denominator. So 187, this is going to be, it's going to be pretty much the same. Because I say, all right, when they say rationalize the denominator, really they just mean get rid of the root in the denominator. And we all wish it was as easy as just erasing the root. Like, oh, what if that 5 wasn't there? Oh, that'd be nice. Okay, I'm done. Well, no, they don't want you to just erase it because you've changed the problem and you've changed the value of this expression. They want you to keep the value of the expression, just make it look different. So since the root 5 is the problem here, it's not the root 3, because we don't mind seeing roots in the numerator. It's roots in the denominator that are bad. I'm going to multiply like we did in the last one, top and bottom by that root 5. Just whichever is giving you the trouble, you know? But it should work kind of similar. Let's see. So in the numerator, the 15 is outside the root. He has no one to interact with. But the 3 and the 5 are both inside. They can multiply to make 15. In the denominator, we have a 4 that's outside. And then the 5 times 5 that's inside. You could write 25 or 5 squared. I'm just going to get used to writing 5 squared for later problems. But a square root and a square cancel. So you're just left with on the bottom 4 times 5, now that the 5 has escaped. In the numerator, there's nothing to do, because 15, nothing can escape from 15. You know, if you try to prime factor it, it's not going to simplify. So numerator is as good as it gets, and the denominator, 4 times 5 is 20. And now that I see the things outside the root, 15 and 20 they're both divisible by 5, I can go ahead and divide them. 5 goes into 15 3 times, goes into 20 4 times. This can be written as 3 root 15 over 4. So believe it or not, that's the same exact thing as what we started with. The same expression, if you put it in your calculator. It's crazy. All right, in 188, this one, it looks different. Like, what? It's not even, there's no root in the denominator. Well, I guess a fraction inside a root is bad too. Like if you were to split this into 2 roots like we've done before. Oh, now you have a root in the denominator, so it's, you know, equivalent to having the same problem. But actually, this one, if you want to, you can simplify that root first, because the square root of 8 can be simplified, because 8 is what? 2 times 4. 4 is 2 times 2. And since this is a square root, we only need a pair of 2's to escape. So it's root 3 on top. A 2 gets to escape, but there's one odd man out because we only needed 2 2's to escape, and there was a third one that didn't really get involved. So that's probably what I would do first, is if it's possible, simplify any roots and then think about rationalizing the denominator. So now, like in the last one, I say, all right, what's the problem here? It's not the root 3, because a root in the numerator is fine. It's the denominator that we don't like to see a root. I'm multiplying top and bottom by the root that's the problem, the root 2. So in the numerator, root 3 times root 2, they're both in the root, so they can multiply across and give you 6. In the denominator, there's a 2 outside, and then there's a 2 times 2 inside. That'll make 4 or 2 squared. Oops, I'm going to write 2 squared. And that way I can see, okay, the square root and the square will cancel. So there's a root of 6 on the top. A 2 was already outside in the denominator, but that 2 that was inside escaped now because the square root and the square canceled. So it ends up being 2 times 2 on the bottom, which is 4. Beautiful. Okay. So next guy. These ones are more complicated. Notice the rationalizing the denominator problems we've seen so far, they've all been square roots. This is a cube root. So these ones are more difficult. It's definitely, I think, worth going back and reviewing these in our notes. So we're not going to go into as much explanation in detail because it would take too long, but think about right now I have 1 7 in the denominator. In order for the magic of the last problems to happen, I want the root and the power to cancel. So what I need in the end, I want to see a fraction that looks like something with the cube root, and I have a 7, so I want 7. But I want the power on the 7 to match the index, so I'd like it to be a 3, because that's the only way that they're going to cancel. So look at what I have. I only have 1 7 right now, but I want 3 7's. So I have to kind of think more about what do I need to multiply by. If I just multiply by 1 7, for example, okay, like this, cube root of 7, then that's 1 7 I already had, plus another 7. That's only 2 7's though. If I have 2 7's, it's not going to escape the root because I need as many as the index tells me. I need 3. So I actually need to give it 2 more 7's, top and bottom. That way the 1 I started with and the 2 I'm giving it will make 3, which is exactly right to escape the root. So on the numerator there was 5x outside, and then a cube root of 7 squared inside now. In the denominator, cube root of, okay, 7 to the 1 times 7 squared, that's 3 7's total. And now, since those are the same index and power, index is 3, power is 3, it cancels. If those were not the same number, they would not cancel, and you'd still be left with a root, which is not good. But finally now the denominator is, oops, it's kind of confusing down here. But finally, yeah, the denominator now is 7, because the root and the power canceled. And the numerator, it's ugly, and there's not much you can do with it, but I don't know. As long as the denominator doesn't have a root. You could leave that as 7 squared, or you could just write 49. I don't know, it kind of looks cleaner as 49. The whole point of writing it as 7 to a power was to try to see if it escaped the root. But we know that this is not going to escape because the power is 2, the index is 3, they're not the same. Ugh. Right, this one is going to be sort of the same type of thing, except the denominator is more complicated, 4 and y. But this one's actually better in a way, because whereas in the previous problem the denominator started with only 1 7, it's almost like, okay, here it looks like we have 1 4, or you can think of it as I have 2 2's, because 4 is 2 squared, get it? You know what I mean? Yeah, if you're feeling like, what the heck? How do you know to do that? I would definitely go back to the notes or the lecture video from this section. What section is this? 10.4. Because this is something that's easy to forget, but it's definitely going to be on the test. And I would probably write a note about this on the on your note card. Okay. So what do I want? I think if you can visualize what you want to see, what's going to allow you to have the root disappear from the denominator, then you're going to do a lot better. So what I want here is I want the denominator, since there's a cube root, I can't get rid of the cube root until everything inside of it has a cube power. Like that. That's the only way. So as it is, I have a 2 to the second, but I want a 2 to the third. That way the cube root and the cube will cancel. I have a y to the 1, but I need 3 y's in order for that y to escape the root. So I just think, all right, starting off, I have 2 2's, but I want 3. So how many more 2's would I need? Just 1. Because the 2 that were already there, plus the new one I'm giving it, will make the 3 I want. As for y's, I only started with 1 y, but I want 3. That means I need 2 more to get there. The 1 I was given, plus the 2 I'm adding to it. That's how you determine what to multiply by. And the numerator always has to be multiplied by the exact same thing as the denominator. So it's not like I want the numerator to look this ugly, it's just to make the denominator look pretty, I'm going to have to make the numerator look terrible. Let's see what happens now. Okay, down here. In the numerator we have, okay, cube root of, there's 11 times 2, that's going to make 22, and then a y squared. In the denominator we have 2 2's times 1 more 2 is going to make 3 2's, so it'll be 2 to the third. We had 1 y, we're giving it 2 more y's to make 3 y's. Okay. And you could just say everything escapes right now, but if you want to be really careful, I would go, well, the numerator's fine, but for the denominator I'd probably go give the 2 its own root and give the y its own root. And then it's really clear, okay, that everything does cancel. A cube root and a cube cancel, a cube root and a cube cancel. So your answer is the same numerator, but the denominator is just 2y, since the 2 escaped and the y escaped. And then it's tempting, but don't try to cancel these y's, because the one in the numerator is inside the root, the one in the denominator is outside. Same with the 22 and the 2. One's inside, one's outside. They can't reduce or interact at all. Okay. Let's see. These ones I think are actually easier somehow. Adding and subtracting roots. Let's see. We got 5 cube root of 4y plus 2 cube root of 4y. So just remember that we can only add or subtract. Subtract roots with the same index, first of all, and these do have the same index, they're both cube roots, but also the same, what they call radicand, which is what's inside the root. So it has to be exactly the same index and same thing inside the root. The numbers in front don't have to be the same, like this 5 and this 2, it's fine that those are different, but the fact that they're cube roots has to be that way, and the fact that they have both a 4y inside, that's perfect. But the way to think of it is, if it's been a while, think of this as like you're adding almost like 5x plus 2x. You know, because it's 5 times some root plus 2 times some root. You add their coefficients, right? 5 and 2 make 7, and you don't change what's left, you just change the coefficient. So this is going to be 5 plus 2 is 7, and you're not changing what's inside the root or the index. So that's it. You just want to do this, you just want to add, or I guess if it was subtract, you would subtract coefficients. Don't change the radical. Yeah, much like if you had variable terms like we did before, 5x plus 2x. You would say, oh, 5 plus 2 is 7, but you wouldn't say x plus x is x squared or something like that. You just say x is x. So it's kind of similar. You don't change the radical, you just change the coefficients. So with that in mind, we're going to try 192, which, although I notice I want to subtract these, but the things inside the roots aren't the same. They're radicands. One is 75 and one's 3. So I'm not able to subtract these yet, but the idea is maybe I can simplify one or both of them, and then maybe they'll be able to be subtracted. So 75, that's a big number. I have a feeling I can probably break that down. Let's see, 75 is what, 5 times 15? Or 3 times 25, however you want to think of it. 15 is 3 times 5. And since this is a square root, I just need 2 of a kind to escape. There's 2 5s. Okay, so that means that the 2 that was already outside is going to be multiplied by a 5 that's escaping the root. And there's an odd man out, there's 3 that has to stay inside. So that'll make 2 that was already outside times the 5 that escaped makes 10 root 3. And I would try to do the same thing with the second radical, 9 root 3, but the square root of 3, that can't be simplified. If you try to break 3 down like we did with 75, nothing's going to happen. But now they're like terms, so it's 10 root 3 minus 9 root 3. It's like 10 minus 9 is 1. So you could say it's 1 root 3, but 1 times anything is that thing, so you might as well just write root 3. Perfect. Alright, and then we got like a souped up version of that guy here. Pretty complicated. But we're going to try to do the same thing. I think all 3 roots, 50, 18, and 32, can all be reduced. We'll try to do one at a time, maybe 50 first. Just because, you know, we read from left to right, so we might as well do math from left to right, I guess. 50 is 2 times 25, or you could have done 5 times 10. 25 is 5 times 5. And then since this is another square root, I just need 2 of a kind to escape the root. So 5 times 5. Okay, one of the 5s escapes, but that odd man out, 2 has to stay inside. Just according to this guy. 2 5s, a pair, so one of them gets to escape, and the odd man out, the 2 has to stay. Alright, let's try something similar for the middle guy. This one, though, has a coefficient of 2. I can't forget him. But the 18, I'm going to try to break down. 18 is what? 2 times 9, or you could do 6 times 3. 9 is 3 times 3. Okay, and again, that's a square root, so I have 2 of the same prime, 3. So a 3 gets to escape. He's going to multiply by the thing that was already outside. And there's a 2 that's kind of the odd man out, because he didn't have anyone to pair up with to escape the root. So since those are multiplying, that's going to become 6 root 2. Maybe I'll just bring this guy down. Yeah, if there was a number in front of the first root, the 50, then that 5 that escaped would be multiplied by that. But since there was nothing, it's just the 5. That's it. Alright, last guy. And I'm hoping we can finally combine all these guys. 32, let's try to break him down. 32, I think of 2 times 16 when I see that. But that's also 8 times 4, huh? That would work too. 16 is 2 times 8. 8 is 2 times 4. Oh my gosh, this is going to take forever. And 4 is 2 times 2. Alright. But I only need 2 of a kind to escape the root. So here's one escapee, and here's another escapee. So actually, 2 gets to escape, and another 2 gets to escape. But one guy has to stay inside. Poor little guy. Sorry, we said. Let's see. 2 gets to escape. Another 2 gets to escape, but one last 2 has to stay inside. So the 2 times the 2 outside will make 4 root 2. Alright, I think we're good. Now we can just add. So think of this, since they all have the same root, they all have a root 2, you're just adding the coefficients. 5 plus 6 makes 11. 11 plus 4 is 15. And then don't change the root like we said before. Beautiful. Alright, I think we're doing good here.